Welcome to the deep dive. We're diving deep into the stack of sources you sent our way, all revolving around something truly, well, mind-bending: black holes. Now, we usually picture these as cosmic vacuum cleaners, right? Just sort of devouring everything in their path.
The standard image.
But your material presents a wildly different idea that these gravitational monsters could actually be the most powerful, efficient energy sources in the entire universe, potentially unlocking energy on scales we can, well, barely comprehend.
That's the core paradox this material really digs into. Our mission today is to unpack exactly how something so dark and, destructive in our conventional understanding could be framed as the ultimate power plant. It's about looking at the science, the theories, and frankly, the sheer scale of energy involved, based entirely on the insights presented in the sources you've shared.
Okay. Let's start with the basics then. What is a black hole, according to the material we're looking at?
Your sources define it pretty clearly as a region of space-time where gravity is just so intense nothing, not even light, can escape. They typically form from the catastrophic collapse of supermassive stars. It's a key prediction of Einstein's general theory of relativity.
Right, standard definition.
But the crucial point, right from the beginning of your sources, is that under specific circumstances, black holes don't just consume. They can actually store vast amounts of energy and, critically, release it.
Right.
Release it in ways we might, theoretically at least, be able to harness.
Which, yeah, feels completely upside down compared to the common perception. So if not just falling in, how do these sources suggest you could actually get energy out? They mention a couple of mechanisms, but seem to focus on two main ones for, advanced civilization.
That's right. There's a theoretical idea involving Hawking radiation, which is tied to quantum mechanics near the event horizon, but your sources quickly pivot. They move to what they seem to consider more plausible for a technologically advanced society, tapping into accretion disks and something called the Penrose process.
The Penrose process. Okay. Now, this is where things start to get really clever, isn't it? This was proposed by Roger Penrose back in, 1969?
That's the one, 1969.
So what's the core concept he came up with? How does that work?
Well, he theorized that if you send a particle into the ergosphere, and that's a specific rotating region outside the black hole's event horizon, mind you.
Okay, outside. Got it.
It could split into two parts. One part would fall across the event horizon, lost forever, but the other part could actually escape. And here's the kicker. It could escape having absorbed some of the black hole's rotational energy.
And the key is, the part that escapes has more energy than the original particle you sent in.
Yeah.
More than it started with.
Precisely. You've essentially used the black hole's intense gravity and its spin as a way to boost the particle's energy. The sources use a great analogy. It's like a gravitational slingshot. But instead of just changing direction or speed, you're actually extracting energy from the black hole itself.
Huh. Extracting energy from the spin.
Yeah. The material suggests this process, particularly harnessing the rotational energy of spinning black holes, is one viable theoretical path forward.
Fascinating. So you're tapping into the spin energy, but the sources, they seem to put even more emphasis on the other mechanism you mentioned, the accretion disks.
They do, yeah. Accretion disks are pretty consistently highlighted as the most powerful potential energy source discussed in this material. You have to picture these incredible luminous whirlpools of gas, dust, and plasma just spiraling inward towards the black hole. Really dynamic.
And as all that material gets closer and closer, what happens to it? Does it just fall in?
Well, before it falls in, it's subjected to just immense friction and gravitational forces. This heats the material up to unbelievably high temperatures. We're talking millions, even billions of degrees. And because it's so hot, it emits vast amounts of energy across the electromagnetic spectrum. Everything from radio waves right up to powerful X-rays and gamma rays.
Right. And this is where the efficiency numbers discussed in your sources become absolutely staggering. I mean, we often hear about nuclear fusion, the process powering stars like our sun, as being incredibly efficient. It converts something like, 0.7% of mass into energy?
Right. And that 0.7% powers stars for billions of years. It generates all the heavier elements.
Yeah.
It's definitely impressive by our usual standards.
Sure.
But the material points to calculations, like those by Kip Thorne back in 1974, suggesting that accretion disks around black holes can achieve efficiencies of up to 40%.
40%? 40% of mass converted directly into energy. That's just huge.
It's revolutionary, really. As the sources explicitly state, that's more than 50 times the efficiency of nuclear fusion.
More than 50 times?
Yeah. Think about that scale difference. It just fundamentally changes the game when we talk about energy generation. Tapping into this kind of gravitational energy release is Well, it's on a completely different level than nuclear processes.
And this isn't purely theoretical anymore, is it? The sources mention actual observations backing this up.
Precisely. That's a key point they make. When the Event Horizon Telescope gave us that iconic first image of a black hole in 2019,
Yeah, I remember that, M87.
exactly, the observations of intense radiation, powerful magnetic fields, and those high-speed matter jets shooting out,
Yeah.
it all provided concrete evidence. It aligned perfectly with the picture of these incredibly energetic accretion disk systems that the theories predicted.
So the physics seems to check out, at least broadly. And the speculative applications discussed in the material, tapping into that kind of power, I mean, what would that even look like?
Well, your sources talk about the possibility of building megastructures,
Hmm.
maybe something similar in concept to a Dyson sphere, but designed to fit around a black hole's accretion disk. The idea would be to capture this immense radiation output. We're discussing potential power sources that could be billions of times stronger than anything we can currently generate on Earth.
Billions of times stronger. That kind of immense power naturally leads you to think about the future trajectory of civilizations, doesn't it? The sources bring in the Kardashev scale here.
Yes, exactly. The Kardashev scale is a way of categorizing civilizations based purely on the amount of energy they can harness and use. So, Type I uses all the energy available on its home planet. Type 2 harnesses the total energy output of its star, like building a Dyson sphere around its sun.
And type 3.
A Type 3 civilization commands the energy of an entire galaxy.
Okay. And the material you provided makes a direct link here, suggesting that black hole engines are considered the potential gateway to achieving that type 3, that galactic level status.
It's presented as a compelling argument, yeah. When you consider the sheer number of black holes, billions estimated in just our galaxy, let alone others,
Billions, wow.
and especially the supermassive ones lurking in galactic centers, they present these ready-made, incredibly powerful energy hubs scattered throughout the cosmos. The material even references specific proposals, like one from Novikov and Frolov back in 1989, theorizing about building orbital power plants around black holes.
So you've got billions of potential power stations, plus these supersized central ones at galactic cores. But the sources also venture into even more speculative territory, artificial black holes.
Right. Now, this is really pushing the boundary of current physics, but it's definitely discussed in your material. The idea is creating incredibly tiny, perhaps stable black holes using, say, future particle accelerators. The theory, which goes back to work by Don Page in 1976, suggests these mini black holes wouldn't be permanent. They'd evaporate pretty rapidly via Hawking radiation, emitting energy as they decay.
Ah, okay. So instead of capturing energy from a black hole's accretion disk or spin, you're capturing the energy the black hole emits as it basically disappears.
Exactly. And because this Hawking radiation converts mass directly into energy, you see it, the efficiency could be almost 100%, theoretically. So they would be these ultra-efficient power sources, albeit requiring just a monumental feat of engineering to create and contain them in the first place. It's presented very much as a far future, highly theoretical frontier.
Harnessing this kind of power, whether it's from these cosmic giants or tiny artificial ones, sounds incredible. But the sources are also quite clear-eyed about the immense risks involved, aren't they?
Absolutely. And they should be. This isn't a power source you'd want to, toy with lightly. Miscalculation could obviously be catastrophic. You have the tidal forces near a black hole that can stretch anything, including spacecraft or structures, into long, thin strands. That's what's vividly called spaghettification.
Right, not pleasant.
Not pleasant at all. And the extreme gravitational fields themselves just pose immense engineering challenges. Building anything, or even just operating safely in such an environment, is incredibly hazardous. The sources emphasize that.
And if we're talking about actually creating artificial black holes, even tiny ones, that seems to bring up a whole other level of concern.
It certainly does. The sources specifically mention the ethical considerations around containment. I mean, the idea of generating something that could, in theory, consume matter unchecked, even if it's microscopic. It raises profound questions about responsibility and safety on a scale we've never really had to consider before.
Yeah, that's a big one. Beyond the practical dangers and these containment ethics, though, the sources really push the boundaries with some truly mind-bending philosophical implications, too.
This is where the conversation gets really interesting, I think. If a civilization could actually tap into the energy density and the bizarre gravitational effects of black holes, would it strictly be for power generation? The sources suggest exploring ideas like using them for computational purposes, harnessing their unique properties near the event horizon for information processing somehow.
And because black holes warp spacetime so dramatically, there are ideas floating around related to time dilation.
It's exactly. The potential for extreme time dilation near a black hole's event horizon could theoretically be used for things like, well, long-term memory storage or information archiving on cosmic timescales, keeping information safe for eons. The sources even touch on really speculative far future concepts about black holes as potential escape routes or maybe information refuges against the eventual heat death of the universe.
It paints a picture of a civilization interacting with the cosmos on a level that's just, yeah, hard for us to even imagine right now. The sources end the section with a truly profound image. Kind of a final thought on this.
Yeah, they pose the question, could the ultimate form, the ultimate legacy of intelligent life, maybe billions or trillions of years from now, be these vast, silent black hole computation engines just drifting through the cold, dark universe?
Yeah.
It's a really striking thought experiment presented in the material, you know?
It really is. So pulling back from that deep speculation, this deep dive into your source material leaves us with a really powerful central idea. Black holes, far from just being these cosmic drains we usually imagine, are theoretically the most potent, the most efficient energy sources out there.
Incredibly dense, astonishingly efficient, yeah. And offering power on, well, a truly galactic scale.
And the provocative thought from the sources, the one that definitely sticks with you after exploring all this material, is this. Maybe, just maybe, in the unimaginably distant future, black holes won't be objects we fear. They'll be objects we farm, something for you to ponder.